Okay, in this video we're going to be talking about the normal distribution. That's section 6C. Okay, so here we'll look at basically what the normal distribution is, what it looks like, and also we'll talk about things like the standard z-score or standardized z-score and other things. Okay, so here the normal distribution arises so frequently that we give it specific attention in statistics. The normal distribution is usually depicted as a bell-shaped curve. And as you can see, we do have two examples of what the bell-shaped curve is and what it looks like. Here, this bell-shaped curve has a larger standard deviation. As you can see, the hump is shorter. That means the spread of the data is wider. Now on this side, we have a smaller standard deviation. You can see the hump is taller and skinnier. When that happens, that means the spread of the data is very small. Okay? Keep in mind the standard deviation talks about the spread of the data. Okay. Now let's talk about the normal distribution. The normal distribution is a symmetric bell-shaped distribution with a single peak. Its peak corresponds to the mean, median, and mode of the distribution. Its variation is characterized by the standard deviation of the distribution. Okay, so if we look at example 1, let's say I want to consider the following set of 3 distributions, all of which are drawn to the same scale. Identify the 2 distributions that are normal. Of the 2 normal distributions, which one has the larger variation? Okay, in this case, I can tell you that graph B would not be a normal distribution because a normal distribution has to be in the form of a bell-shaped curve. So I can eliminate B altogether. And in this case here, I see that A and C are normal distributions. So here I'm going to choose this answer choice, A and C. Okay. Now, of A and C, which one has the larger standard deviation? Well, the one with the smaller of the 2 humps, if the hump is smaller, that means that the standard deviation has to be larger. And in this case, it's going to be C. So C has the larger standard deviation. A has the smaller because the hump is tall and skinny. Okay. Alright, next we'll look at the conditions of a normal distribution. So what is considered to be a normal distribution? A data set satisfying the following criteria is likely to have a nearly normal distribution. Most data values are clustered near the mean, giving the distribution a well-defined single peak. And the ones that we looked at have only one single peak. Data values are spread evenly around the mean, making the distribution symmetric. Okay, so that means when it's symmetric, the left side of the normal curve has a mirror image of the right side of the normal curve. Number 3, larger deviations from the mean are increasingly rare, producing the tapering tails of the distribution. Okay. And usually a larger distribution where that hump is getting smaller. You have a shorter hump in the normal curve. And number 4, individual data values result from a combination of many different factors. Okay. So now in example 2, here we want to state whether you would expect the following data set to be normally distributed or not. And in this case, we got scores on an easy statistics exam. Well, if we're dealing with an easy statistics exam, then that would mean that that everyone should get an A on that exam if it's an easy exam. So here, it would not be a normal distribution here. Okay, so here those scores would not be normally distributed because pretty much everyone would get an A on a very easy statistics test. Okay. All right, next we're going to look at the standard deviation in a normal distribution. All right, because all normal distributions have the same bell shape, knowing the mean and standard deviation tells us a lot about where the data values lie. A simple rule, often called the 68, 95, 99.7 rule, gives approximate guidelines for the percentages of data that lie within 1, 2, or 3 standard deviations of the mean for any normal distribution. Alright, and this is what a normal distribution is, and here you can see the mean is at the center, and then we got within 1 standard deviation of the mean. And I'll show you this in color since it's better to see it that way. Here you can see the darker green represents the data values within 1 standard deviation of the mean, and then a lighter green within 2 standard deviations of the mean, and then a much lighter green will be within 3 standard deviations of the mean. Okay, now what does that 68, 95, 99.7 rule states? Okay, here it is right here for a normal distribution. That means about 68%, or just over 2/3 of the data points, will fall within 1 standard deviation of the mean. And then about 95% of the data points will fall within 2 standard deviations of the mean. And then about 99.7%, or almost all the data points, fall within 3 standard deviations of the mean. So that rule, the 68, 95, 99.7 rule, applies to data values that are exactly 1, 2, or 3 standard deviations from the mean. Okay. Now we're going to apply that rule to this particular example. Here we're going to assume that a set of test scores is normally distributed with a mean of 120 and a standard deviation of 25. Use the 98, 95, 99.7 rule to find the following quantities. And in this case here in part A, we got the percentages of scores less than 120, and that's going to be equal to what percent? So what percent of the data values will be less than 120? Okay, so in this case here, what I want to do here is draw an illustration of a normal curve. And it looks like this. It's not the best, but here's going to be the best I'm going to be able to do here. The center will be right here. That's your mean, which is going to be, in this case, under 20. Okay. Now we know we got within we got within one standard deviation of the mean above and below. The standard deviation was given to you as 25. So if I go one standard deviation above 120, that means I'll add 120 to the 25. I'm going to get 145. And if I go one standard deviation below, that is 25 subtracted from 120, that's going to give me 95. Okay, and then next, go another standard deviation above and below. That will be two standard deviations above and below the mean. So here I'm going to add another 25. If I go up 125 to this 145 will be 170. And then I'll subtract another 25 from the 95. That will give me 70. So between 70 and 170, that represents two standard deviations from the mean, above and below. Now, go 3 below and 3 above. Well, I got 170, and the standard deviation again is 25, so if I add that 25 to the 170, this will be 195. And then for 3 below, subtract 70 from minus 25, you're going to get 45. That's what my normal curve is going to be. Now, we want the percentages of scores less than 120. Well, 120 is the mean. That's the center of this entire data set. And here it separates the normal curve into two equal parts. Everything under the curve represents 100%. Okay? So, if we want scores less than 120, that's going to be this bottom half right here. That's this area to the left of 120. That's going to be half of 100%, which is 50%. And they say around the one decimal place as needed, so it'll be 50.0 when you type that in. Okay? So here, if I did this, okay, as you can see, there's 120. That bottom half is the 50% that is below 120. Okay? Alright, part B. The percentage of scores greater than 145. Okay? Greater than 145 will have to be, and if I cover this up, will have to be data values that are to the right of 145. So here's 145 right here. If I cover that up, I'm looking for this part right here that's to the right. Okay? Now, let's think about this for a moment. 145 is one standard deviation to the right of 120. And 95 is one standard deviation to the left of 120. So anything within one standard deviation of the mean from 95 to 145, according to the 68, 95, 99.7 rule, that has to be 68% of the data values that are within one standard deviation of the mean. Okay? Now, let's look at this. I'm only focusing on this part right here. That's one standard deviation above. And this is split evenly from one standard deviation below, to one standard deviation above. All of that is 68%. So in this case, if it's split evenly, I need to divide by 2. That will give me 34%. So from the mean up to one standard deviation above the mean, that's going to be 34%. But I want this area to the right here. Well, I know at 120, that splits the normal curve in half. So the left is all 50% and the right is all 50%. So here, let's take 50%, subtract from it that 34%. And that will give me 16%. That's going to represent this area to the right of 145. So the percentage of scores greater than 145 is 16%. Okay. All right, now part C is the percentage of scores between 70 and 145. In this case, between 70 and 145. Well, here's 145, and this is 70 right here. Well, I know this. Between 70 and 170, that's 2 standard deviations. That's within 2 standard deviations of the mean. That means, according to that rule, 95% of the data values are within 2 standard deviations of the mean. Okay. Now, here we're going to think of the bottom half right here. Up this way. So if I split, okay, now, if this is within 2 standard deviations of the mean from 70 to 170, then if I split this in half, divide 95% by 2, that will give me 47.5%. Okay, because between 70 and 170, that's 95% of all the data values that are within 2 standard deviations of the mean. So here we need to take half of that, since we're dealing with the 70, because that's 2 standard deviations below the mean. Alright, next at 145, that's 1 standard deviation above the mean. Okay, so that's 68% of the data, but we need to take half of that. So 68%, divide that by 2, that will give me 34%. Okay, so now to find the the percentage of scores between 70 and 145, that sits right here, I need to add these two together. The 47.5% to the 34%. And that's going to give me 81.5%. So to answer that question, 81.5% of the scores will be between 70 and 145. Okay. Alright, next we'll look at this example. Assume the resting heart rates for a sample of individuals are normally distributed with a mean of 75 and a standard deviation of 15. Use the 68, 95, 99.7 rule to find the following quantities. And in part A, we want to find the relative frequency of rates less than 105 using the 68, 95, 99.7 rule. Now, in this case here, we're looking for the relative frequency, so we're not looking for a percent, we're looking for a decimal value. Okay? So in this case here, I'm going to go ahead and draw that normal curve just in case, so we can get an idea of what's going on here. The mean is in the center. The mean was 75. The standard deviation is 15. So if I go one above and one below, one above I need to add 15 to the 75. That's going to give me 90. One below, subtract 15 from the 75, I'm going to get 60. And then for 2 standard deviations above and below the mean, Well, add 90 to the 15, you're going to get 105. And then to find 2 standard deviations below, subtract 15 from the 60, that'll give you 45. And then next, 3 standard deviations above and below. Well, above the mean, add 15 to the 105, you'll get 120. And then 3 standard deviations below, subtract 15 from the 45, you'll get 30. Okay, so now let's answer part A by finding out the relative frequency of rates less than 105. Well, here's 105 right here. We want the rates less than that. Notice that 105 is 2 standard deviations above the mean. 2 standard deviations above the mean. And I'm going to mark off 45 right here because between 45 and 105, that's within 2 standard deviations of the mean. And according to the rule, 95% of those data values are within 2 standard deviations of the mean. Okay, the whole area underneath the curve, underneath the normal curve, is 100%. So I want to find out what this area and this area is equal to. If I subtract 100 minus 95%, that's going to give me 5%. Okay, so this area on the left and on the right is 5% total, but they're split evenly. So if I take 5%, divide that by 2, we're going to get 2.5%. Okay? Or 2.5% as a decimal will be 0.025. If you take 2.5, divide that by 100, you're going to get 0.025. Now, to find out what the rest of this area is to the left of 105, all of this from here all the way to the end, we know that total area is going to be 1 whole, or 100%. So if I subtract 1 minus 0.025, I'm going to get 0.975. So here, the relative frequency of rates less than 105 using that rule will be 0.975. Okay. Now part B, the relative frequency of rates greater than 90 using the 68, 95, 95.7 rule. Greater than 90 will be anything to the right. Okay, that's this part that's to the right. So in this case, I know 90 is 2 standard deviations above the mean. And I also know that from 60 to 90, it's 1 standard deviation above the mean. And I know from 60 to 90, that's within 1 standard deviation of the mean. And 68% of those data values are going to be within 1 standard deviation of the mean. So I'll use that. Okay? Now I know the total area under the curve is 100%. So if I do 100% minus 68%, that will give me 32%. Okay? So on the left of the red line and on the right of this red line, that's 32%. And they're split evenly again. So here we're going to take 32%, divide that by 2, you're going to get 16%. Now 16% as a decimal will be 0.16. Take 16, divide that by 100, you'll get 0.16. So in this case here, now they say the 3 decimal places, so I need to carry that out to 0.160. And then finally, part C, the relative frequency of rates between 45 and 75 using the 68, 95, 99.7 rule would be how much? Well, 45 is 2 standard deviations below the mean. And according to this rule, 95% would be within 2 standard deviations of the mean, 95% of the data values. And I'm only finding this area below. I'm dealing with a number below the mean, so divide 2 into 95%, you're going to get 47.5%. Okay. And now, I know something else here. 75 is the mean. Okay. 75 is the mean right here. So I'm finding the area between 45 and 75. Okay. And guess what? That represents the 47.5%. Or 0.475. Okay. Because of course 75% is the mean, so that means that there is no standard deviations above or below the mean. Okay. So that's how we find the relative frequency as a decimal. Okay. Alright. Let's look at this one. Applying the 68, 95, 99.7 rule. Now here we can apply the 68, 95, 99.7 rule to find the approximate answers to many questions about the frequencies or relative frequencies of data in a normal distribution. Like this one in example 5. The scores on a psychology exam were normally distributed with a mean of 64 and a standard deviation of 4. A failing grade on the exam was anything 2 or more standard deviations below the mean. What was the cutoff for a failing score? Approximately what percentage of the students failed? Okay, so here I will draw a normal curve to see what's going on here. Now the mean was 64 and the standard deviation is 4. So if I'm going to be 2 standard deviations below, that's 1 to the left and then 2 to the left, 1 standard deviation below 64, well, that's still 4, represents standard deviation. So the score that is 1 standard deviation below 64 will be 64 minus 4, or 60. And then 2 standard deviations below that, subtract 4 from the 60, you're going to get 54. I'm sorry, 56. 60 minus 4 is 56. Because the standard deviation is 4. Okay? So now, a failing grade on the exam was anything 2 or more standard deviations below the mean. So, if a student had a score of 56 or, well, anything less than 56 was failing. Okay? And what percent of students failed. In this case here, I know this is 2 standard deviations below the mean. Okay? Now, according to the 68, 95, 99.7 rule, within 2 standard deviations of the mean would be 95%. Well, we're dealing with the bottom half. So here we're going to take 95, divide that. Actually, we can do this. We don't need to divide by 2. We can subtract 100 from 95. 100% from 95. Okay? Because that will give us this bottom area right here. Because anybody that falls in that area would fail. This will be 5%. But again, we're dealing with the bottom half, so that means we take 5%, divide that by 2. That would give us 2.5%. Because see, the 5% represents not only this area, but also this area to the right. But we only want the one on the bottom, far left. So we divide by 2. So that means approximately 2.5% of the students failed. Okay. So that's how we deal with the 68, 90, 95, 99.7 rule to answer these particular questions. Okay, now next we'll look at standard scores. Okay, the number of standard deviations a data value lies above or below the mean is called standard score or z-score. And that's defined by this. Z, which is your standard score, that will be equal to the data value minus the mean divided by the standard deviation. Okay? Your Z is going to be the data value minus the mean divided by the standard deviation. Now, if the data value is above the mean, the standard score is going to be positive. Now, if the data value is below the mean, then your standard score will be negative. Okay? So, in example 6, the scores on a psychology exam were normally distributed with a mean of 57 and a standard deviation of 9. What is the standard score for an exam score of 70? Okay, so let's identify what we already got in this particular example. Alright, we're told that the mean was 57 and the standard deviation was 9. And we want the standard score for an exam score of 70. That's going to be your data value. So to find what our z-score is going to be, we got to do the data value minus the mean. I'll go ahead and write all this out. Data value minus the mean divided by the standard deviation. So here your z-score is going to be this. Okay, your data value is 70 minus the mean 57 divided by the standard deviation of 9. Now we first got to do 70 minus 57. That will give us 13. And then do 13 divided by 9. And here they want this to the nearest hundredth. In other words, we need to round this off to 2 decimal places. So if we do, let's say 13 divided by 9. That would give us, to 2 decimal places, 1.44. So the standard score would be 1.44. Okay, here's another example. Pull the page down. The scores on a psychology exam were normally distributed with a mean of 55 and a standard deviation of 9. What is the standard score for an exam score of 59? Okay, so here the mean was given to you as 55, and the standard deviation, I'm going to abbreviate this as SD, was 8. The data value that they give you, because they want you to find the standard score for an exam score of 59. Okay, so here we're going to use that Z formula. Z is equal to the data value minus the mean. That's 59 minus 55. All that's divided by 8. Okay, 59 minus 55 will be 4. And if you do 4 divided by 8 on the calculator, you're going to get 0.5. But to 2 decimal places, we must say 0.50. Now, what that 0.50 means, that the exam score of 59 is 1/2 of a standard deviation above the mean of 55. That's what that means. Okay? So like in that last example that I did, here, that 1.44 means that the exam score of 70 is 1.44 standard deviations above the mean of 57. And here's one more of these. The scores on a psychology exam were normally distributed with a mean of 70 and a standard deviation of 6. What is the standard score for an exam score of 74? Okay, so here, that mean that was given to us was 70. The standard deviation was 6. And the data value 74. And now we want to find that Z-score, or that standard score for the exam score 74. So here, your Z is going to be the data value minus the mean. That's 74 minus 70 divided by your standard deviation of 6. Well, if I do 74 minus 70, that will give me 4. And then 4 divided by 6. Okay, and I'll put this up here so that you can see what's going on here. 4 divided by 6. To 2 decimal places, it will have to be 0.67. Okay, so that means the score, the exam score of 74 is 0.67 standard deviations above the mean of 70. Okay? Alright, now, let's talk about standard scores and percentiles. The percentile of a data value is the percentage of all data values in a data set that are less than or equal to it. You often see this on test scores when they give you a percentile. Percentiles usually tells you the percentage that scored lower than what you got on a certain standardized test, like the ACT or SAT, things like that. A data value that lies between 2 percentiles is said to lie in the lower percentile. We can convert standard scores to percentiles with computer software or a standard score table. And on the next page, you're going to see what a standard score table looks like. Here it is. This is the table for standard scores and percentiles for a normal distribution. Here your z-score is on the left, both positive and negative, from negative 3.5 up to 3.5, and the percentile that's associated with it. Okay. So we're going to use that particular table to answer these questions here in example 9. Here we're going to use that table to find the standard score and percentile for the following data values here. Starting with part A, a data value 2.2 standard deviations below the mean. In this case here, as you can see, now in the homework they're going to tell you to click on the icon to view that standard scores and percentiles for a normal distribution, which is that table that I just showed you. Okay, now the standard score in part A, it says a data value 2.2 standard deviations below the mean. If it's below the mean, it has to be a negative 2.2. So the standard score is negative 2.2. And the percentile is, well, let's find negative 2.2 in this table. We look to the left, find negative 2.2. Go to the right, you'll see that percentile, 1.39. Okay. That's how we find the percentile here. Now part B, the standard score for a data value 1.6 standard deviations below the mean. Again, it's below the mean, so that 1.6 has to be negative. So it'll be negative 1.6 standard deviations below the mean. And the percentile is, let's find negative 1.6 in the table. Well, oops. Sorry about that. Negative 1.6 is here. The data value here is 5.48. So the percentile for negative 1.6 is 5.48. And then part C, the standard score for a data value 1.4 standard deviations above the mean. Well, above means that it has to be positive. So here, the standard score will be 1.4. And then we're going to find 1.4 to determine what that percentile is. So here's 1.4 way over here. That percentile is 91.92. 91.92. Okay. Okay, and then the final example in this video also, well, it deals with percentiles, but here they're giving you the percentile. You'll have to find out what the standard score is going to be. So here you're going to be reading the table backwards. Okay? And you're going to find that you're not going to get the exact value here. You're going to have to pick one that's closest to it. Like in this one, you're going to use the accompanying table of standard scores and their percentiles under the normal distribution to find the approximate standard score of the following data values. Then state the approximate number of standard deviations that the value lies above or below the mean. Okay, so in part A, we're looking at a data value in the 90th percentile. Okay, now we're not going to find 90% in this table that I'm going to show you. What you're going to have to do here is select a value that is closest to 90%. Okay? And by looking at this, the closest value to 90% will have to be this one, 90.32. That's going to be closest to 90% as we're going to get. And then read to the left for that corresponding z-score. In this case, it's 1.3. Okay, so the standard score for the 90th percentile is 1.3. So here, in this case here, the 90th percentile lies approximately 1.3, because a z-score means it's that number of standard deviations, and in this case, since it's positive, it's going to be either above or below the mean. And they'll give you a choice here. So here it's above the mean. Okay. Alright, now part B, a data value in the 60th percentile. Well, in this case, we're not going to find the exact 60% in this table. We need to look for, in the percentile column, a data, a percentage that's closest to 60%. In this case, I will pick this one where it says 59.87. That's closest to 60%. The z-score that corresponds to it will be 0.25. So in this case here, a standard score for the 60th percentile is approximately 0.25. Now, the other part, the 60th percentile, lies approximately, and a z-score means that is that number of standard deviations here, 0.25 standard deviations. Since it's positive, it's going to be above or below. In this case, above. It is positive. So we're talking about 0.25 standard deviations above the mean. And then finally, part C, the standard score for the 67th percentile is approximately what? Okay, let's find a decimal value that's close to 67. Well, 67.36 will be close. The z-score for that will be 0.45. Okay, so here we're going to have 0.45 here for the standard score representing the 67th percentile. And notice the 67th percentile is going to be 0.67, 0.45, because that's your z-score. Yeah, 0.45. And that's 0.45 standard deviations. It's positive, so it's going to be above the mean. Okay. Alright. So, this will conclude this particular video on the normal distribution.